So hello everyone, I'm Zhezhou Sun. Welcome to my talk. Today I will present to you StructCurves, interlocking block-based line structures. This is a collaboration work with Devin Borcon, Emily Whiting from Dartmouth College and Boston University. So industrial zippers are commonly used to bind materials in our daily life, and they are convenient for assembly without additional instructions and can adapt to curved surfaces. However, their flexibilities means they cannot maintain a specific shape once assembled. These limitations inspired our research question. Can we create rigid structures that are as easy to assemble as zipping a zipper? Our research builds on several foundation works. Notably, Schuller's zippable shapes concept demonstrated 3D shapes formation by zipping 2D developable surfaces, inspiring our interest in user-friendly 3D construction methods. While some studies focus on 3D shapes from laser-cut planar parts, our approach utilizes line structures as a skeleton framework, allowing for various material integration in 3D shape building. To achieve a rigid structure upon assembly, we are inspired by Sneffen's work on interlocking mechanism using prismatic joints. Each component has two joints inserted in different directions, which create an interlock. Subsequent pieces interlock with existing ones, ensuring that once the final two pieces are glued together, the entire structure is securely locked. One challenge in this prismatic joint design is that the piece detach during the disassembly because they interlock through translation motion. Since the piece detach, this means construction involves a collection of many disconnected pieces, and keeping track of them, their assembly order is hard. To address this, we developed a new interlocking mechanism using revolute joints. Instead of translating into position, new pieces rotate into place. This design maintains a constant distance at the pivot point, making it possible to add connectors that chain the pieces together. In our case, we use a fabric mesh as the connector. The fabric mesh can bend in any directions while helping to maintain the consistent distance between pieces on the same side. The advantage of using two chains for assembly is that it embeds the assembly order for easier construction. Let's use an example to demonstrate how the interlocking works. For example, take R1. Two revolute joints are inserted into it from R2 and R3. This joint limits its movement. For R1 to escape, it has to rotate around two different pivot points in opposing rotation directions. Rotating around two different pivot points is impossible, and therefore R1 is locked in place. As each new piece is added to the structure, it becomes key to the assembly, interlocking the pieces below it. Here is our first straight structure curve prototype utilizing this mechanism. Two sides are flexible when disassembled, and the structure is assembled by layering pieces from both sides one by one to form the straight structure curve. As you can see, the two sides remain flexible during assembly, but once fully assembled, this structure becomes rigid and is capable of supporting heavy weight without too much deformation. The next challenge is, can we use this mechanism to construct complex 3D shapes? Users can describe the shape with a cubic Bezier spline curve. In addition to the shape, we also need to specify the orientation of the teeth. But defining such orientation in 3D space can be hard to control. To simplify this, we introduce our orientation control parameter, theta. Here is how it works. We define reference frames along the curve using finite serrate frames, which consist of tangent, normal, and binormal vectors that change based on the curve's curvature and torsion. At each point along the curve, we rotate the normal vector of the reference frame by the angle theta, which determines the final orientation nz at that point. Users only need to specify theta at the control points, and our program smoothly interpolates these values to create a continuous orientation along the curve. This method allows users to control the complex orientations with a single, easy-to-manage parameters. Given a Bezier curve as input, we developed a Blender plugin that automatically generates the structure curve. Users can design the curve in Blender and adjust the orientation at each control point to achieve the desired shape out of their mechanical or aesthetical consideration. Next, they can choose to apply templates to generate the final structure curve. We included 2 different templates based on the interlocking mechanism with revolute joints. Once finalized, the program flattens the structure onto 2D planes. Importantly, there is no strict limitations on the target shape size, as the program automatically breaks the flattened size into segments. Each segment fits within user-specified printer's volume. But when assembled, the final structure can exceed the printer's build capacity. And now it's time for fabrication. During this printing process, to keep the correct ordering of pieces and strong enough bindings between them, we embedded a mesh to serve as connectors. The embedding process works as follows. The first few layers are printed as usual. Then we post the print to place the mesh. The layer right above the mesh is over-extruded, allowing the extra material to penetrate the mesh and fuse with the lower layers, creating a strong enough bond. Next, I will demonstrate the potential of our structure curve by showing its 3 key features through examples: its compactness, load bearing, and its abilities to transform between flexible and rigid states. With structure curve, we designed a packable chair with compactness ratio of 7:1. This chair can be stored in a small glass container, but when assembled, its size exceeds the build volume of our 3D printer. Structure curve can also be applied to garments. Here, we present a transformable dress. When the underlying structure curve is disassembled, the skirt hangs naturally. However, when the structure curves are assembled, the skirt is elevated, creating a floating appearance. Beyond fashion, structure curve can also be used for personalized spine support. In this application, we 3D scanned our user's back and designed a structure curve that perfectly fits his spine. When disassembled, the structure curve allows full mobility, but once assembled, it provides firm support to the user's back. Let me finish this. We also demonstrated the potential of a structure curve in larger scale applications. Using it as a skeleton, we built a 1.5 meters long boat wrapped in water-resistant tarp. In a buoyancy test, the boat successfully supported 27 kilograms of bricks and toys. We also conducted a series of simulation and physical experiments to validate our design and assess structure curve strength. For instance, we set up equipment on the left to measure the displacement at the center of the structure curve when subjected to pushing or pulling forces. We also added some experiments to prove that our structure will stay interlocked even without the mesh. For more details, please refer to our paper. In conclusion, we present a pipeline that generates line structures using our novel revolute interlocking design. These structures remain flexible when disassembled, but interlock into 3D curved, shape-retaining, and load-bearing forms, simplifying assembly and enabling compact transport. This makes them ideal for large-scale developable structures and usage scenarios like in clothing. Thank you.
Cool. Ken Nakaki from U Chicago. Beautiful work, really cool idea. I really love the joint interlocking mechanism. I was wondering if you thought of like some ways that this could be employed for like self-assembly mechanism? For example, maybe the thing could be still passive, but it looks like maybe by like some like shaking methods, it could like interlock automatically and like you could break it. But I don't know. I know that's hard, but have you thought about like how you could extend this?
Yes, I think we have considered this before, and but now for the current template we designed at here, it's hard to achieve this. But we, in the future works, we are considering to add a slider to such kind of structures, or maybe just do the passive way, like you described. I think that will be a good potential things to try.
Great, thank you.
Well, great work. Yuichi, Hirose, CMU. I really loved your work. And how difficult is like it to apply this to like a right angle? Because this kind of reminds me of this space filling things. So yeah.
You mean how to determine the orientations of these shapes?
I mean like bend to this, like to achieve this right angle things. Like is it, how hard would it be? Like this is like, so this should be like some curvature limitation, I think, but how difficult is it to apply this to like right angle?
So we have examples there, and you can try it in the poster sections. And because our programs can automatically flatten the shapes to the 2D planes, and while keeping the correct while keeping the shape of the regular joints. So in general, it's not too much troubles when assemble them. It's no difference comparing to the straight zippers. Yeah, but you will see that it's a little bit tricky to assemble them for some cases, especially for the sharp turn shapes.
Thank you.
Hi, this is Willa from UChicago. Really love your work. Wonder if you tried printing them in different sizes, and whether like how difficult it is to, or how important it is to adjust the tolerances of the interlocking mechanism for different sizes.
Yeah, so we have tried to print them for all these applications. They are in different sizes, and we have tried to enlarge each piece. And in our experience. So for now, in the template we provided for users, they are fixed to like about 3 centimeters large, but we can definitely print it larger. And this won't affect the interlocking mechanism. But as for the tolerance, currently we would suggest the users to use about 0.6 millimeters for the shapes we provided. And for the large scale the structure curves in the larger scales, we would suggest users to maybe try with different other tolerances to see what works best for them.
Okay, thank you.